This is a quick online version of Lab 1 for natural disasters, which is about using and interpreting and extracting data from topographic maps. If you look on the home page of natural disasters and go to the content section, lab assignments and lab syllabus, and the map reading folder, you'll see several materials. One of them is an answer sheet, which I'll show you when we have answers to put on it. Another link is a YouTube video that gives information about this mapping tool called ArcGIS Online in general. And you probably don't have to look at this right now, but if you're interested, you might have a look. But it won't really be necessary. I'll be able to show everything you need for this week in this lesson. And then there's two other links here. One is to a web map or a story map that summarizes the topic, and then there's a live usable web map from which you'll gather data to fill in your answer sheet. So let's look first at the online lesson, which is this, and I include this just for completeness. It's a standalone discussion of topographic maps and the process of using them to calculate important values such as slope, elevation, etc. The dual purpose of this first week's exercise is to teach you how to use a topographic map to get elevation, slope, and some other data, which we'll be using throughout the semester, and also to introduce you to ArcGIS Online, a web mapping system. So a couple of tools, so to speak. So this is a topographic map. Landscapes are three-dimensional. To represent them as two dimensions, one trick that can be used is to create this idea and use this idea of something called contour lines. Contour lines are lines of equal elevation. Everywhere on one of these brown lines on this map is an equal elevation. So for instance, the 2,800 foot line travels right along here, and everywhere on that line is the same elevation. There's a brief illustration here of how to help you also understand topo lines. This is a hill, or a schematic of a hill, and just to show that there can be a person climbing on the hill, a little stick figure. If one draws lines around the hill at equal elevations, 100 feet, 110 feet, 120 feet, you would see from the side view of the hill, you'd see each of those elevations, the bottom of the hill, the top of the hill, and the other bottom of the hill. Now if one were to look straight down on the hill in a plan or map view, the whole contour of each elevation would be visible. You wouldn't see just this stripe, this side of it, but you'd see the whole 100-foot elevation contour. What is interesting about this particular illustration is that you can see that from A to B, the hill is sort of steep, and from B to C, it's very steep. And then that's reflected in the visualization that from A to B, the contour lines are kind of far apart, and from B to C, they're kind of close together. So this is a steeper area, and this is a flatter area, and that's the top of the guy's head. This one you should just go ahead and skip. There's a tool in the web mapping system, which I'll demonstrate, a measure tool, and this slide just illustrates where that is. Elevations can be determined just by looking at the contour that a particular point that you're interested in corresponds with. A is right on top of the 700-foot contour line. Everything on this line is 700 feet in elevation, so A is 700 feet in elevation. B is, well, each of these dark lines, there's a dark line every 100 feet in elevation, and there's 5 steps in between each heavy line. So each of these lines in between is 20 feet. So that one's 700, 720, which generally isn't labeled, only the main ones are labeled, 740, 760, 780, and 800. So in this case, 700, 720, B would be 740 on this particular map, and C would be 720, 740, 760, 780. So C is in between 60 and 80. So C would be 770 by interpolation. Another thing that can be done with a topo map is computing a slope. And you may remember from some previous course in math or geometry that a slope is equal to the rise, change in elevation, over the run, the distance traveled. And I'll show you one example of calculating a slope by rise over run. And finally, this is a snapshot of the actually a partially live map that shows a place out in the Finger Lakes, Bristol Hills area, and it has a variety of points, and the lab exercise is to answer several questions and put them on the answer sheet. So I'll do a few of them for you so you can see how this works, and then leave you to do a few more yourself. What's here is a completely live interactive map with the points on it. It has the usual tools to zoom in or to zoom out on the map, and you get different map series, different versions of the map depending on the scale as you zoom in. I think there's 4 series. You can see the topographic lines. I am going to turn off these generic notable features which are used for another exercise. And we can see the various points. That takes us back to the home, and the measure tool is visible. Now we can go ahead and take a quick look at what it wants us to answer. So question number 1, what is the distance from A to B? So a relatively simple task of measuring a distance from A to B. First we have to find A and B. You can do that by zooming and panning. This is called panning. So measure the distance from A to B. And in this case all we have to do is see A and B. Use the measure tool, which is up here. And by default it picks area. So we'll go with distance. And it's useful when doing things that are mathematical or numerical, especially if there's going to be a computation, to use the same units for everything. So right off, even though we could use anything, we're going to go with feet and use feet continuously throughout this exercise. So I select feet, and I can measure from A to B or B to A, which would be the same. And it says 13,680 feet. Oops, I need to double click. 13,680 feet by using the measure tool, where I hold down the mouse key, draw a line to the destination, and watch the distance. So I'll do that one more time. Maybe I can measure any distance. I can measure the width of this valley by clicking and holding. Nope, I guess I click and let go. Click, let go, draw the line, click again, and double click to lock and end that measurement. 3,420 feet. I could also click, drag. I could measure a long irregular path by clicking again and again as I go. And there my total path is a certain distance. Double click to end a path. So that's how to measure distance. So the first one, I did mention it. One advantage of a video lesson like this is you can go back and review, or slow it down or speed it up. Next thing it's asking for is the elevation of point C and the elevation of point D. So C and D. I'll go back to the back to this map, and I'll close that and clear everything. I use the house, and I can look for C and D. there's point C right there. And in order to get best results, I can also roll the wheel on the mouse and zoom way in. And if I zoom in far enough, I discover that point C is placed right at a benchmark point at the very top of a hill. So here's 2040 elevation, 2060, 2080, and the highest point on this hill, which is centered around here, is actually point C. Point C is 2,083 feet. That was an easy one. We didn't have to look at contours, although the contours make sense and are consistent. Next I want to look at point D, which is way down toward the bottom. And zooming in on point D, zooming and panning, we do have to go ahead and use the contours on this map. And we can see that there's a 2,000 foot contour right there. And moving upward, higher, since higher is we're getting to be higher elevations, we move up to 2,100 feet, moving in this direction. That's 2,000, 2,020, 2,040, 2,060, 2,080. So that's 80, that's 60, and D is in between the two. So perhaps we could go ahead and say 2020, 40, D is 2,065, because it's part of the way from 60 to 80. That's 80, that's 2,100, and I assume both of these two are 2,120. But point D is 20, 2020, 2040, 2060, plus a few more feet. So that's the use of those values of these, reading the contours. It's relatively simple concept, but actually following a contour around and eyeballing it takes a little bit of focus and concentration and practice. It's not a difficult concept though. Going back to the answer sheet, it also asks, what is the slope from point E to point F? What is the slope from point E to point F? In order to determine those values, I wonder if I have a notepad here anywhere. I'm going to write these down for myself and then show you the computation later. But to get the slope, we need to know several things. We need to know the elevation at point E. We need to know the elevation at point F. Then we need to subtract to get the difference in elevation, the rise between them. And then we need to get the distance from point E to point F. Then we can get the slope. So why don't we go ahead, go back to our map and get the two elevations, E and F. Back to our map, go to the home, and there is E and F. And there's a good view of it all. So this is the top of a hill. So we're going downhill in this direction towards a river or towards a highway which runs through a valley. So this line is 1,800 feet. Point E is one thin line lower. So point E is 1,780 feet in elevation. You could go the other way. This is 1,600, 1,700, and then count up 1,720, 1,740, 1,760, 1,780. So E is 1,780 feet. Point F seems to fall right on a dark line, which is one whole dark line below this. Point F is 1,100 feet. And the difference between the two then is 680 feet. You could, if you wanted to be meticulous, just say count the actual stripes between the two and directly get a change in elevation by going 1,000 feet, 2,000, 3,000, hundreds, 100, 200, 300, 400, 500, 680 feet difference by just counting the stripes that are crossed from one point to another. That's one way to do it. Or you could get the elevation here and subtract to find the difference in elevation. Now we can go ahead and use the measure tool, and I will ask for the distance in feet, and I can click and click, and I get 3,121.8 feet. And I'm writing that down on a piece of paper to use in a minute. Well, now given that we know the change in elevation, 680 feet, the distance, 3121.8, I can visit my calculator. There it is, my computer calculator, and I can divide rise over run, or change in elevation over change in distance, by going 680 divided by 3121.8, and I end up with a slope, just in fraction, of 0.2178, or if I multiply by 100, I get a slope of 21.8, would be a good number of significant figures to report this as. So I'd get a slope of 21.8% because I multiplied by 100. So that fills in the slope from point E to point F. What I'm going to leave you with to practice on is to use your own skills to get the distance from G to H using the measure tool. Pretty straightforward. Looking at contours to get the elevations of I and J, and finally doing the whole process of finding a slope from K to L. Elevation at K minus the elevation at L divided by the distance between them. So that covers half the answers, and it actually covers half the answers and covers all of the content.